Perfect. Well, I assume everyone can hear me pretty well. Thank you all for having me over here. And so for today, I'm going to be talking about star formation on a scale that hasn't been quite covered in this conference yet. And namely, we're talking about the scale in which the assembly of molecular clouds are well resolved. So you can understand what's going on. So a quick overview, in simple terms of star formation, we often think of star formation as a process where a self-gravitating cloud collapses due to gravitational instability, and of course, in the center you form the protostar, and due to conservation angular momentum, you form a disk around it, which are the precursor of planets and so forth, which has been talked about in some of the earlier talks. But one thing to keep in mind is when you think about molecular clouds, they're substantially larger than these self-gravitating cores, what we call dense cores. And they're about 0.1 parsecs in diameter for the most part. And if you think of molecular clouds, they're roughly a few orders of magnitude larger and also a few orders of magnitude denser than your average molecular clouds. So what we're really interested in is how exactly do molecular clouds assemble these dense cores that can go on to form stars and planets. And if we take a step back, realize that molecular clouds are actually highly hierarchical. And so what we find is these dense cores tend to be embedded in filamentary structures, and they're not finding isolations. And if you zoom out a bit further, you realize that these structures live in molecular clouds. And so molecular clouds is actually ubiquitous with filamentary structures. And unfortunately, the color scheme doesn't quite show well. But in the sense that one of the main findings in the past decade or so is molecular clouds full of these filamentary structures. And when you compare two simulations, for example, you realize that it's actually fairly easy to make filaments just simply by having supersonic turbulence in molecular clouds, and that's just natural consequences of it. And when you turn on gravity, you can basically start to form structure that resembles observations quite well and start producing stars. And so the general consensus from these pictures is that in order for clouds to assemble dense cores, what you need to happen is basically you have turbulence that basically forms filaments either as initial seeds for further accretion or simply these continuation of turbulent flow as what assembled the mass. And once you have these filaments, you can fragment into dense cores, and that forms the dense cores and potentially sets the initial conditions to give us the initial mass function. And so understanding the details of how you exactly assemble these structures in molecular clouds has important implication on understanding of star formation. And so while a lot of work has been done looking at structural comparisons from the dust thermal continuum emission and also doing structural analysis on thermal stability, one key information that really will allow us to explore further is the gas kinematics. And so as shown in an example here on the left-hand side, you could have the fairly simplistic, purely gravitational case. In that case, you can have gas that's basically being accreted onto the filaments. In that case, you expect the flow to be fairly perpendicular relative to the geometry of the filament itself. In a more realistic, complicated case, you could have MHD simulations. In this case, you expect the gas to be coupled to the magnetic field. In that case, you can basically expect the gas flow to be channeled by the magnetic field onto the overdensity in the cloud structure. And as that overdensity grows through accretion, you can imagine it can start to distort the magnetic field, and that itself has implication on how to change the gas flow directions. So how exactly are we going to trace these gas flows, and what's the type of molecular tracer that's appropriate? So for a lot of extragalactic work, most of you are familiar with producing CO as a tracer, which is pretty good because CO is fairly abundant, and of course for that reason, actually fairly bright. But at the scales that we're probing in which the dense cores and filaments are actually formed, they typically are optically thick for the more common isotopologues. In the case even for C18O, where you expect things to be optically thin, for the most part, if you look at the left-hand graph where you plot the integrated density of 18CO as a function of column density, you seem to actually kind of plateau in the intermediate column density, and that seems to be a function of chemical depletion and a few other effects going on. Whereas in the middle, what we can use is actually ammonia, which is considered to be a denser gas tracer. In this case, you can see that it correlates quite well with the denser gas as you continue to go on to higher column density regions. And in addition to that, ammonia is actually quite a good tracers in terms of gas kinematics, because you can actually observe multiple rotational states with the same inversion transition within the same observation. So calibrations are taken care of, and you can actually measure temperature quite well. But for the rest of this talk, I'll mostly focus on the gas kinematics. So along with that comes the Green Bank Ammonia survey, and furthermore, there's also the other surveys, the keystones that use GBT to observe ammonia. And as you can see from the center integrated intensity map, you can realize that ammonia traces the dense gas quite well when compared to the Herschel column density on the left. And if you look at little star symbols on the map, you also realize that these dense gas are the ones that directly engage in star formation. That's where you find the embedded protostars are. And of course, on the right-hand side, you can show that these give you, when you fit the kinematic models to it, you can extrapolate a beautiful velocity centroid map. And that's actually where our focus will look at for this particular work. So to showcase, you can see this is where the gas survey has observed in nearby molecular cloud to Perseus, where the dashed line shows the footprints of observation, and the black contour shows where the ammonia is detected. But one thing we also discovered is that with these kind of sensitivity, not only do you detect simply just one component in the gas, even with a dense gas tracer, you actually need a component to fully describe the emission that you're getting. And well, in some cases, you actually have two dense structures that just happen along line of sight, as you expect for three-dimensional structures of the cloud. A lot of it, what you're seeing is actually ambient cloud, basically a large velocity dispersion background clouds that seem to be tracing the gas reservoir that you may be creating in dense structures. So these sensitivities are actually quite important to really bridge the scale between how do you draw the gas from the reservoir into the dense filaments. And so this is just an example of the Perseus East region, and you can kind of see where the structures are. And so with two multiple component fits, the beauty is that you are now empowered with the ability to decouple confusion along one site. And so what we did is identify structures using, in this case, a CRISP, the density rich identification algorithm to pick out the filament spines. And from there, you can actually assign membership to what we consider as velocity coherent or velocity continuous structures. And so from their example that's been shown, it's basically we can assign membership on the left-hand side where you see the ridge of the spines of the filaments, as well as a velocity central map produced by these coherently identified structures. And from there, you can actually take two-dimensional velocity gradient maps and decompose that locally into the perpendicular and parallel component. And that's what's shown in the right and the left and center panels. And so to look at how it behaves, we can basically just say, what is the medium property of each filament? In this case, when we draw a comparison between the velocity gradient of the perpendicular and parallel component, shown in the left and right, plot against the velocity dispersion, realize there's actually seems to be a correlation. And that seems to suggest, it supports the picture that these velocity gradients seem to be tracing accretion flows, and what you're seeing is accretion flow are driving turbulence. So you have accretion-driven turbulence that basically increases with the rate of accretion. Another thing we can quickly plot to kind of verify that is how does the velocity gradient compare to the mass per unit length of each filament. And so what that tells you is basically two things, the gravitational potential of the filaments as well as the evolutionary stage of the filaments, basically how massive they are per length kind of thing. And so for perpendicular direction, we actually realize that there seems to be a correlation between two properties, but not so much for the parallel. And that makes sense in the sense that if you expect the accretion to be driven by gravity onto the filament, then you would be driving the perpendicular component. But for the parallel one, we expect things to trace either fragmentation to cores that are on the fairly local scales, or transportation towards a hub is either related to more local potential that's not related to filament, or more global potential that's outside the filament. So far, these kind of global properties seem to suggest that we do actually have a picture where the accretion flow in the filaments grows these filaments. But picture of that is far from over because we're looking at a single dish and mostly chasing what usually considered the classical width of filament about 0.1 parsec. But when you zoom out into larger clouds, especially in an example like the Orion molecular clouds, you realize the entire cloud itself is actually fairly filamentary. And these quote-unquote 0.1 parsec filaments seem to be embedded throughout these large cloud structures. And on the smaller scale, if you look at it with ALMA in N2H+, you realize that even these more typical filaments can be resolved into bundles of smaller subfilaments. Each of them actually have fairly substantially lower width than what's typically quoted earlier with the lower resolution study. And so indeed, when you actually zoom in onto the GBT ammonia surface resolution with ngVLA fed of GBT data, you start to resolve these filaments into substructures. In this case of Perseus B5, you see these small structures where things are considered basically start to be fragmenting. In this case, the author of this paper think it's forming a proto-quadrupole system in the fragmentation process. So once you have enough resolution, you realize the picture was actually far from simple, and these hierarchical nature of accretion and fragmentation continue to happen. And so similarly, if we run a similar kind of analysis in finding filament and just simply divide its emission by what we call watershed methods, we can measure the radial profile of these filaments quite well. In this case, realize that they actually behave quite well in terms of they can be well modeled by the Plummer profile with a power law index. But they're substantially smaller than the typical 0.1 parsec filament width. So that's actually one thing that we discovered, it's that it wasn't just simply from the turbulent process. And when we look at the velocity dispersion, trying to get a sense, do we actually have an interesting signature? One thing we discovered is that there seems to be actually increase in velocity dispersion as we move away from the filament spine. And while we've seen these in simulations before, this is actually the first time we were able to look at in observations as well. And there are some basically different ideas regarding what that potentially means. But the important part of it is that a lot of time the universal 0.1 parsec width has been explained by it as just a natural process of as where a cloud reaches the sonic scale as the turbulence cascade from that large scale down. And 0.1 parsec tends to be the case where you can no longer compress the gas very much. So that's how you form the filament. But the fact that these smaller, well-resolved subfilaments are narrower than that suggests that something else is going on further beyond that. And so this really lends a leverage on understanding how exactly do the filaments accrete its mass from the surrounding, and how does it actually fragment into smaller cores and subfilaments that eventually will give us our stellar system. And just to briefly look at it, if we look at velocity gradient, there's actually also a wealth of information. And while I won't go into detail, I just want to point out that there's quite a bit of what appears to be turbulent-looking ripples if you just simply look at the velocity, the magnitude of velocity gradient. And some theories have suggested that you could distinguish between gravitational infall from a turbulent process just simply by looking at magnitude. In this case, one of the highest column density, what they call condensates, we expect to be the seed for dense core, also have one of the outstanding largest velocity gradient. And so that's something that we really want to look into it as well. So long story short, it's once you are fully able to resolve below the 0.1 parsec scales, you can actually see a lot of additional information that truly reveals the full scale of these hierarchical formation of filamentary and core structures. And so while we can actually map those with ngVLA currently, these are quite intensive in terms of resources that we need. And so if we want to do it statistically speaking, we really need a facility at ngVLA where you have the sensitivity to do similar kind of resolution study, but over entire molecular clouds where we can actually start to build proper statistics on what's going on. And furthermore, while we expect the ngVLA to be at least 5 times more sensitive than ngVLA currently, to even truly be able to extend these kind of study beyond the nearby clouds and start to looking at higher mass star forming regions, which could be more representative of a lot of processes going on, both in our Milky Way as well as throughout the cosmic history, we could really also push for potentially the array, receiver array kind of thing on ngVLA, and that would give us a unprecedented capability to basically do these kind of studies, not only in the nearby molecular clouds, but also pushing towards more of a higher mass star forming regions further out from there. And so with that, I will just leave my summary slides on here, and I'd be happy to take questions.
All right, questions for Mike? You get a mic over here, a microphone.
Thanks, Mike. That was a really great talk. So I was intrigued by your velocity dispersion being so much lower along the spine of the filamentary structures. So when you fit the spine, some of what is in there is cores, right? And some of it is presumably things that are still relatively less dense. So is it that the velocity dispersion is lower in the cores and that is bringing down your velocity dispersion, or do you have a way of dealing with filament but not core, or is it hopelessly intertwined?
Right, so I think you asked a pretty good question in terms of fundamentally is there a distinction between core and filaments? And some of the current idea is that there's not really a distinction. It kind of depends on evolutionary stage of the filament. So the idea is that once you form filaments, the local density perturbation is what seeds the core, and you can fragment that further. Alternatively, you could actually have perturbation introduced by basic clumpy accretion, and that could actually produce further cores that wasn't initially seeded. And that has been kind of debated in the literature. And so ultimately, yeah, it's kind of hard to draw this strong distinction between core and filaments. And even in the B5 region shown here, if you look at the velocity dispersion map that's shown on the left, I realize that the entire region is actually fairly coherent and subsonic. And aside from basically enhanced density, there's not a clear distinction between filament and core, especially in a more coincident example like this one.
Do you have any other questions? I see one in the back. Is there anything on Slack?
Hi, Mike. Great talk. So I had a question regarding this increase in velocity dispersion when you go away from the filament. So what we saw, for example, in another region is that when you start resolving like a broad line with that, you sometimes spatially resolving, you get like several filamentary structures with low velocity dispersion. So do you expect that in the outer molecular cloud, you might have a lot of like filamentary structures that you with a thin line with, similar to what you see in the dense filament that you just simply not resolving?
Yeah, and so in this case, so far, it doesn't look like we have substructure beyond basically the filament scale. Eventually, once you get down to sub-core scale, there's actually these streamers I haven't talked about, and that's a potentially related but somewhat different process that's going on. And regarding to some of the other work we're referring to, where you could potentially have large velocity dispersion, that's one thing we're hoping to push for with ngVLA. It's that in the case of Perseus, including Perseus B5, really we only have so far two regions of Perseus that we look at this resolution. It's that the differential velocity between each of these subfilaments are actually fairly close to each other. They're actually subsonic relative to each other, and they seem to be embedded into a larger parental structure. The other work that is even being looked at, which is predominantly CL, one, it's tracing larger volume density just due to the different kind of tracer, and two, it's from very different clouds. So we do occasionally see other examples where unresolved filament could be basically resolved spectrally into large velocity dispersion structures, but without actually pushing for statistical study to say, is this fairly universal, as well as can we do apples to apples comparison with the similar tracers? It's a little hard to tell if the ones we're referring to is the same as the one we're seeing here. And like I said, it'd be nice to really push for with ngVLA to get a statistical sample and should get a sense of, are some of these outliers, or do they basically align on spectrum of different class of object?
All right, we're about out of time. Is there a last quick question? All right, if not, let's go ahead and thank our speaker again.